Hello, I'm Benjamin Purvis, and this is our presentation based on a novel CubeSat platform for monitoring space weather. This paper focuses on creating ways to study and observe the effect of space weather on CubeSats. Minimal data has been collected on this topic. This paper focuses on current technology we have to prevent space weather and its downfalls, utilizing current technology to collect data, which will allow us to better understand space weather, how we can transform that data into new technology, and finally, how the new technology will save big corporations money and decrease their contributions to orbital debris.
The WCDT has done so much in the past few years. We started by writing proposals, then got one selected. The team was selected in 2019 to launch their first 1U CubeSat, the WCDT-1 into space, aboard the Falcon 9. Once this started up, the school began to write more and more papers. The team also launched multiple high-altitude balloons. While doing this, we are getting data when the buoy lands in the water as it bobs up and down. The team got another paper selected called the CubeSat. This CubeSat is testing lithium-ion polymer batteries to capacitors and will be launched aboard the Falcon 9 in the fall of 2021. The team has also gone to many conferences and presentations, such as doing SmallSat in Utah. During COVID, the team has continued to attend virtual conferences and write papers. The team is starting to attend things in person, but it will take a while to get back to the way things used to be. The team also attended the annual Florida Space Day event in Tallahassee.
Space weather describes variable conditions in space that may have an ill effect on satellites and ground technology. Space weather is highly dependent on the sun's solar activity cycle. The cycle occurs approximately every 11 years, where there is a period of low activity, called solar minimum, followed by solar maximum, when the most space weather occurs. There are three different types of space weather: flares, solar energetic particles, and coronal mass ejections. Flares are caused by bursts of electromagnetic radiation. The flare's light is accompanied by X-rays and other electromagnetic waves. Solar energetic particles accompany flares. Lastly, a coronal mass ejection is the sun's release of solar plasma and a magnetic field. Coronal mass ejections can be made up of billions of tons of magnetized matter. Most solar weather arriving at Earth is deflected by the magnetosphere and atmosphere, but some weather does reach Earth as solar weather events. In 1859, the English astronomer Richard Carrington documented and published observations about the event, which became the benchmark for more recent solar weather events on Earth. The Carrington event, as it is known, included a solar flare, geomagnetic storms, and a solar energetic particle flux. It had a catastrophic impact on the telegraph surface. If the Carrington event had struck Earth today, it would cause more damage. National power grids, communication, and aviation will all suffer. On the ground, space weather causes blackouts by damaging transformers and creating high voltage instability. High-frequency communication systems that are necessary for commercial flights to travel over the polar regions may be disabled. In those cases, scheduled flights are routed away from the poles for days, and mobile network performance may also suffer. In a 2003 space weather storm, 10% of 450 active satellites reported a failure. There is continual research in the design of commercial satellites to tolerate radiation from the Van Allen belts and space weather. CubeSats, however, are more susceptible to the ill effects of space weather than commercial satellites. Energetic charged particles and plasma material coming mainly from solar winds and coronal mass ejections are trapped in the Earth's magnetosphere. This plasma may decay a CubeSat's orbit. Almost all the velocity attributed to the force of the plasma CubeSat collision comes from the CubeSat's own orbit. The only speed attributed to the plasma is its thermal motion. As such, a collision with one charged particle produces an insignificant force to change the CubeSat's momentum or induce orbital decay. On the other hand, there is some likelihood that a CubeSat can encounter a stream of plasma called an ion current. The ion current may have a negative impact on the CubeSat's momentum. Another consideration about drag attributable to plasma is if the CubeSat's solar panel has a negative bias voltage, it will attract more plasma. This situation will cause orbital decay for the CubeSat earlier than expected. Lastly, alongside space weather, one should consider the deorbiting effects of Earth's atmosphere. Although the force of Earth's atmosphere is insignificant above 700 kilometers, as a CubeSat's orbit decays, the force grows exponentially. The major factors of drag caused by air are the CubeSat's velocity and air density.
Solar sails are something that capture energy from light particles. The light particles bounce off the reflective sail. When it strikes the reflective sail, it creates energy. Solar sails can cost as low as $20 million to get a small demo of one. Solar sails are also a current method to slow down the process of orbital decay, which is where CubeSats decay in space, and they have a longer lifespan by using solar sails. They usually cost around $60 million, but this can go all the way up to $170 million, depending on how big you need the solar sail to be. Solar sails are composed of thin, flat material called mylar, which is a reflective material that is sometimes used for decorating, but is also an electrical insulator. Mylar was originally used for musical instruments, but is now used for solar sails. Solar sails are around 160 meters big, but again, this can vary on how big you need the solar sail to be. But this is about as big as a dishwasher or bigger, and usually weighs around 70 pounds. Solar cells do not use the wind to go and move, but instead use solar energy, which they use to go and thrust. Solar sails do not use fuel, so therefore their payload does not have to be as big and is more cost efficient, because you do not have to build, test, and fly as big of a payload, which fuel is not easy to carry into space, nor is it cheap. Solar sails have a downfall, though. Its downfall is that while going around the sun, solar sails have solar pressure, which is pushing and pulling you at the same time. This makes it very hard to travel in space with the solar sail.
To analyze space weather, few technologies have been picked. These technologies are aerogel, altimeters, accelerometers, and silicon particle detectors. The reason why aerogel was chosen was because of its size, weight, and cost. Aerogel is very small. If the aerogel would go on one of the sides of a 1U CubeSat, for instance, it would only cost roughly $100, and the weight of the aerogel would only be 0.015 grams. In a CubeSat, a weight restraint is something that cannot be overlooked. Knowing that there's a technology so lightweight and cost efficient makes this technology different from others. Altimeters and accelerometers work hand in hand. When particles collide with the spacecraft, friction begins to act on the satellite. The satellite then slows down, which this is where you can use the accelerometer. When the spacecraft slows down, the altitude decreases, so you can use the altimeter. These technologies don't have anything special. They are great at what they do, and they can fit inside a small satellite. And the high density of where most particles are can be calculated due to changes in speed and altitude at specific times. Lastly, I chose silicon particle detectors. This is because it is more well known than other particle detectors, and the way the silicone detectors work make it very beneficial. The silicone slows down the particles, and it has a timer inside, and it's calculating the rate at which the particles collide into the detector. This technology is very efficient, and with a right attitude control system, this can be very beneficial to understanding the rate of the sun's coronal mass ejections. The purpose of this study is to develop accurate data towards how space weather works. Very little data has been collected on this topic, and it is only in the form of pictures. Raw numbers haven't been collected, and this is what this technologies seek to do. Right now, mission lifetimes aren't very long. NASA is building satellites every day that cost about $60 million, and those satellites may only last a year or two. If mission lifetimes were longer, companies wouldn't have to spend money to refurbish the satellites or put new ones in orbit. This can even lessen companies' contributions to orbital debris. Overall, the main focus of this study is to collect numerical data. The most important data, however, is the decrease in altitude. Knowing how much the decrease is We can make technologies that will slow down this effect or bring it to a halt altogether. Other data also is beneficial since it can be calculated utilizing modern day equations to get the decrease in altitude. The other types of data are the acceleration, the decrease in altitude, and the amount of collisions per amount of area. As I said earlier, these all can be calculated utilizing modern day equations to find the decrease in altitude, which is the main focus of this study. Thank you for your time.